I think this is one of the best sessions, actually. We saved the best for last. It's become a little bit of a transition now to have Scott Aaronson actually wrap up Q2B with Ask Me Anything session. We call this session actually Ask Me Anything with a Quantum Computing Superhero, because at some point Scott gave this interview to a reporter doing an article for the Marvel movies that had mentioned quantum. The reporter referred to Scott as Tony Stark without the suit or the money. So I don't know what that means exactly, but since then we kind of kept that, and it's become a little bit of a tradition. As I said, we'd like to welcome Scott back, and we hope to have him again for many, many years. And these are really the two anchors of the Q2B show, right? Having kind of John Preskill kick things off. He provides kind of the gravitas for the event, and having Scott Aaronson provide a little bit of the comic relief and relaxation. So it's true, and I did clear that by him before saying it. So with that, I'm gonna have Scott come up. Scott. So we're ready to jump into questions. No moderators or anything. We'll just kind of, please raise your hand. We have mic runners coming out, and we'll, I'll leave you with Scott. Take care.
What can the quantum computing community learn from the story of AlphaFold and the CASP process? What lessons should we take?
Well, I think the first thing that we could say is that there were remarkable gains that you could get in protein folding, without using a quantum computer at all, right? And so we used this for a long time, as one of the main examples of where we could get a useful quantum speed up. I mean, I use that as an example also, right? The protein folding, and to whatever extent AlphaFold has just solved the problem of protein folding, then to that extent, that is one less thing for a quantum computer to give a speed up for. Now, having said that, I am very far from an expert on protein folding, but I talk to people who know a lot more about it than me, and they say that actually, there are many proteins that are still not handled very well, and there are more complicated ones where, there are quantum effects that are important, and where something like AlphaFold is not correctly capturing them. Okay, and so that's really where I would look for eventual quantum advantage. To the extent that the difficulty of protein folding just comes from the size of the search space, that you are searching among all of these configurations for one of minimal energy. To that extent, I would not expect much quantum advantage there, right? I mean, eventually there's the Grover speed up, but probably no more than that. But to the extent that the difficulty of protein folding comes from some quantum effects that are important for a particular protein, to that extent, I would say this is a good target for quantum advantage, maybe even a relatively near-term one.
So to the extent that ADS, CFT help give us some insights into error correction, do you see any other high energy physics problems that would have some impact on the quantum computing space?
That's a wonderful question. I mean, I certainly hope so. I remember Daniel Harlow and others, were 5 or 6 years ago, where we're talking about that ADS-CFT is which has been one of the central things to come out of quantum gravity, out of string theory in the last 25 years, is literally an example of a quantum error correcting code, right? And not just analogous to one. And they talked about maybe this will even help us to design better error correcting codes that could be useful for quantum computers. And Harlow would have a quip his talks that this could be the first ever engineering application of quantum gravity. Now, unfortunately, that hope has not fared very well. And the reason seems to be that although ADS-CFT is an error-correcting code, it's not really the kind of error-correcting code that you want for a quantum computer. It's sort of optimizing for the wrong things. So it has this property of sort of this sort of local decodability. So like from any given small region of the boundary, you can sort of decode operators that act on this wedge that's defined by that boundary region. So that's a very interesting property for an error correcting code to have, but it's not the one that you need if you're trying to build a useful quantum computer, right? There, you just kind of want maximal smearing out of the information, without any locality, right? So you could say ironically, ADS-CFT falls short as a quantum error correcting code by just not being holographic enough, not being non-local enough. But it has been, just the very fact that connection exists, I think, was an absolutely amazing insight that sort of underscores the centrality of the questions being asked in quantum information. That sort of regardless of what happens with the technology, that these questions are not going anywhere. Now, to your question, what else could quantum gravity tell us about quantum information? There is some work just over the past few years about something called position-based cryptography, where you're trying to prove your spatial position by sending messages and using the fact that the speed of light is finite. So there were protocols proposed for this, making use of entanglement, and then there were attacks against those protocols. Okay, but then people said, but maybe it's okay because the attacks required the different attackers at the different locations to share an exponential amount of entanglement. So that wasn't really a practical attack. Okay, now very recently, I believe Jeff Pennington and others had work where they argued, they gave, let's say, a physics proof that there is an attack using only a polynomial amount of entanglement. Now, amazingly, that proof goes through ADS-CFT. Okay, and in fact, you could say that by the standards of the quantum information community, it is not a proof, okay, or it is not yet a proof, okay, just because it uses all this sort of non-rigorous stuff, and it has not been sort of compiled down to our language. I think it's a very interesting question, whether you can sort of take that argument and de-ADS-CFT-ize it, if that's a verb, right? Just turn it into something that people can understand and verify without having to believe in anything about quantum gravity, right? Then that would be just a direct application then of quantum gravity to a quantum information problem. Other thing, I mean, Lenny Susskind has been talking a lot about complexity geometry, right? So for reasons that come out of quantum gravity, out of ADS-CFT, he has been interested in kind of the metric on quantum states, which is defined by the distance between two states is the size of the smallest quantum circuit that maps the one state to the other state. And you can study this just as a metric, and it gives rise to some crazy kind of hyperbolic sort of geometry. And so he's been studying all kinds of questions about that. Now, he has told me many times that his hope is that this study will then feed back into complexity theory, that it will lead to lower bounds on the sizes of quantum circuits. And and I tell him that that sounds ridiculously optimistic, but that is who he is. That is always what he does, right? And whatever he's thinking about, on a given day, is the thing that will revolutionize science. So, I continue, I think that these connections, are of a nature where, even if you're only interested in quantum information, even if you didn't care about quantum gravity, you can no longer ignore these things, right? I'm these are presented at, just straight, quantum computing conferences like QIP, and it has sort of infiltrated straight quantum information to a degree that I think, 10 years ago I would have regarded as really remarkable.
Um, for the future fault tolerant system, I have a practical question is that, so you need the logical qubit, but as I understand, logical qubit will never have a residual error of 0. So it will be something like 10 to the minus 4, 10 to the minus 8, and you need more and more resources to drive it down to 0. So in your opinion, what is good enough?
Okay, well,
residual.
this question, was asked at the very beginning of the theory of, quantum error correction, quantum fault tolerance, right? 25 years ago, Dorita Haranov, Michael Ben-Or, right, proved the threshold theorem, right? They, and Zorek, Laflamme, others, independently had very, very, very similar results, right? And what they said at the time is what I will still say to you today, which is, an acceptable error rate is whatever error rate lets you make a measurement at the end and get the right answer with a high probability, right? Now, we heard talks I think Peter Chapman's talk, right? IonQ saying, well, we only have to do as much error correction as you need to for a given computation. I would say that is all quantum error correction, right? All of it is like that, right? That's the entire point from the beginning, right? You push the error rate down to like 1 over the length of your computation, and you don't need to push it down lower than that. So it's just determined by how long the computation is, right? And this is stuff that we've understood for 25 years.
Something like 10 to the power minus 4 is acceptable?
Yeah, well, it depends on how long the computation is. If your computation has like T gates, then you're going to want an effective error rate that goes like 1 over T, let's say.
So a bit of the physical world involved in cryogenics, superconductivity, thermodynamic limits to scaling that, problems with, talk about being able to grow that environment. We heard even a comment about the, a cryogenic size of a building in the IonQ talk. What do you see as the barriers going forward with the supercooled superconducting approach?
Well, the barrier clearly is to scale up, right? There are, and I am far from an expert on superconducting hardware or, really any other kind of hardware. But, my understanding is that, you should be able to put a few hundred, maybe superconducting qubits, on one chip that, would go into one dilution fridge. To go beyond a few hundred, on a single chip is going to be difficult. For one thing, the more qubits you put on the chip, the more crosstalk there is, right? The more, higher order correlations there are that you start worrying about, and so then, at some point, you're probably talking about interfacing multiple chips. I would love to sort of see that, see it, explained in more detail how we're going to do that for superconducting qubits. For ion traps, I at least feel like, the problem has been well solved in PowerPoint. I see these beautiful PowerPoint animations with all these ions, shuttling around and turning all these corners, and the lasers, sending them exactly where they need to go, or yeah, right. That will, yeah. Anyway, it looks awesome, right? It's good PowerPoint animation skills, you know, and I hope that we'll see that, right? But I think, you know, with superconducting qubits, you know, on the one hand, you know, they are arguably, you know, the furthest ahead at this moment in terms of, you know, what you can demonstrate, you know, with full programmability, right? You know, in terms of quantum supremacy experiments and so forth. You know, so there's a lot of nice things about it. On the other hand, you know, I don't, you know, from everything I know, you know, the problem of how to scale to, you know, thousands or millions of superconducting qubits has not been solved yet. You know, we should not give, you know, you know, at least, you know, while maintaining the type of gate fidelity, you know, anything like what you would need for fault tolerance. So we shouldn't pretend that it has been. But you know, you know, the nice thing is that, you know, we are now in a world where, you know, if we fail at this, then it will not have been for lack of trying.
Hi, I have a question about random circuit sampling, quantum supremacy, and how it relates to generative modeling, right? Some people have pointed to quantum supremacy as a motivation or inspiration for using quantum computers for generative modeling. And so what I'm wondering about is, do you have some, I don't know, intuition or point of view on what types of distributions you expect quantum computers to be strongly advantageous at sampling from? Or maybe another way of putting this is, if I have some use case that involves, you know, some distributions, how would I convince myself that a quantum computer would or would not be
Yeah.
good at sampling from it?
Yeah, so the existing type of sampling-based quantum supremacy experiments, you know, the ones based on random circuits, for example, I expect that if they are useful for anything, then it is some kind of cryptographic task, right? You know, generating certified random numbers, things of that kind. Or, you know, maybe, you know, some questions of physics interest, like, you know, studying the physics of, you know, random circuits themselves, or, you know, out of time order correlators and things of that kind. Okay, but you know, these are not distributions that are of any particular interest for machine learning or anything like that, as far as I know. You know, in fact, you know, they are designed, you know, almost as just sort of maximal garbage. You know, they are sort of the thing that you get, you know, and I should know this because I was, you know, involved in proposing this stuff in the first place, right? But you know, they are just what you get if you apply a random sequence of quantum operations to just sort of maximally scramble up your amplitudes, and then, you know, take the squared absolute values of those amplitudes and get probabilities. So they're sort of designed to be sort of maximally unpredictable and structureless and featureless, right? Each amplitude looks like an independent Gaussian random variable, right? You know, they're not exactly. There's not enough degrees of freedom there, but they're statistically they look as if they're independent. You know, and so that knowing one should tell you very little about any of the others, right? You know, this is not like the kinds of distributions that would show up in practical machine learning problems, which would tend to have much more structure than that. You know, now you know, with boson sampling, I would say something similar, right? That, you know, these are distributions defined by permanence. You know, I don't know where they would arise. On the other hand, when we look at fermions instead of bosons, right, then you do get distributions which are called determinantal point processes, and those actually do arise in machine learning. Okay, the determinant, you know, used to give you a probability shows up when you have a machine learning model where, let's say, for example, you want to sample a collection of images, but have all of those images be sufficiently different from one another, right? And what you're doing is effectively you're treating the images as if they're fermions, subject to a Pauli exclusion principle, right? And two that were too similar, you know, are going to make the determinant too small. Like, they're going to correspond to vectors that are nearly equal. giving you a parallelepiped of a small volume. Okay, so you need all the things to be all the vectors to be spread out. So fermion sampling actually does correspond to something of very great interest in machine learning. However, fermion sampling does not give you quantum supremacy, because it is exactly the same structure. The structure of the determinant actually makes it easy to solve with a classical computer. But maybe there's something interesting to be done there.
So one question. So under the conditions that, well, some people are a bit skeptical whether full universal quantum computer can ever be implemented. So how do you see the possible advantage from usage of hybrid hybrid classical quantum computer?
Okay, well, the first thing that I would say is that in practice, every quantum computer will be a hybrid quantum classical computer, right? Every quantum computer will have a classical control system, right? And you will be sort of sending the instructions, writing the code, having the user interface, all of that, using some laptop or some workstation that does not have quantum computing inside, but that will be sending signals to a microcontroller, which then sends signals into a dilution refrigerator or whatever that controls the qubits, or that controls ions in a trap, or whatever. So and always we will be using classical computing for whatever classical computing is better at, because why not, right? I mean, I've used the analogy that you can use a quantum computer to do a classical computation. It would be kind of like using the space shuttle to ferry people around a parking lot. Okay, it's just it's like the one thing can simulate the other, but with such a ridiculous overhead that why would you ever do it that way, right? So every quantum algorithm is hybrid. Every quantum computer is hybrid, right? And so now, and I'm not sure if that really helps in addressing the first part of your question, because the question for the skeptics will always be, but did you gain anything by having a quantum part at all, compared to having the thing just be entirely classical? Okay, so that's the question that we have to answer. Right, and quantum computing ultimately only justifies itself in practice if there is a positive answer to that question. Okay, if using our quantum classical hybrid approach, we win compared to an approach that is entirely classical. Okay, and that might sound obvious, but like every day I see another example where that is not heeded. So, like we always have to keep in mind that, yeah, that is ultimately the goal, to beat the best that anyone can do using an entirely classical approach.
Oh, hi. This is a more beginner's question.
Mm.
In one of your blogs or one of your writings, I remember you made a quip, something about when you were a graduate student at Berkeley, you hung out with the wrong crowd, mathematicians, right? And you asked them something about, they said, Aronson, what's wrong with you? It's all about quantum computing. It's all about complex numbers of probabilities, if I'm paraphrasing you correctly. And so the question is, but when we get to density matrices, we've got two kinds of probabilities. We've got relative frequencies, and plus we've got quantum probabilities. And they're different, yet they're together. So
what?
So, I mean, what do you think about that?
What do I think about it? All right.
It's
Well,
like they don't fit. They shouldn't. I don't know.
Okay. All right. Fine. So I guess first of all, I actually, although my memory is getting worse and worse, I do remember the anecdote you were talking about, where I was asking these math grad students why did they think that God, nature, whatever would have chosen the complex numbers for quantum mechanics, in writing the code of the world. And they said, oh, well, come on, complex numbers, they're algebraically closed, right? Of course, and they had that much, intuition into the mind of God to just immediately say that and just move on to the next thing. Okay, so now density matrices, are this incredibly useful mathematical construct for looking at just one part of an entangled quantum system, for example, or looking at a probability distribution over different pure quantum states. Of course, complex numbers still arise there, right? So, the mystery of why the complex numbers, we could ask it just as well in terms of pure states or in terms of mixed states, right? But, the thing about mixed states that has always been philosophically weird, if you like, is that, as you said, I think E.T. Jaynes, the probability theorist, had a famous quote about this, that they sort of scramble together objective and subjective uncertainty in a way that no one has yet seen how to unscramble, the omelet, right? So, it seems like, a pure state seems like an objective thing, which is just out there in the world. We can't know it for certain, but if we knew the right basis to measure it in, then we would get a certain answer with probability 1, which means the fact that the system is in this pure state is just an objective fact about the world, right? A probability distribution, seems like something subjective, right? And a density matrix, generalizing a probability distribution also seems subjective, and we know, there are many examples where just if you learn something new about a system, then you update the density matrix that you assign to it, right? Okay, and then the trouble is that the same density matrix can have infinitely many different decompositions into, distributions over pure states, right? And so then, actually how you represent your density matrix in terms of pure states, that's also subjective, right? I mean, you could say that if you wanted, you could say that there is an objective pure state for the entire universe. But in that case, it would not be observable by any of us, right? That would just be God's pure state, if you like. And for us, I think density matrices are objects that encode they're representations of our knowledge about a quantum system. Right, I think like we have to say that for example, if you want to ponder this more, you can read the writings of Chris Fuchs, for example, who's written thousands and thousands of pages about exactly these issues. He's written enough about it to make anyone's eyes glaze over. Hundreds of times, right? But he just keeps hammering home the point. Well, that quantum mechanics is not about the world, it's about us, right? It's about how do we represent our uncertainty, and using this, non-uniqueness of the decomposition of a density matrix as one of the main planks of this philosophy. Okay, I mean, the trouble with that is like that's all well and good, except clearly quantum mechanics is also about the world, right? Something has to be true about the world such that we would describe it using density matrices in the first place. One could have imagined a priori that the world would have been classical, right? That was a perfectly logical possibility, and we would just use classical probability distributions, okay? So the fact that we have to use this representation at all is something about the world. And, I don't like the philosophies that sort of endlessly defer the question of, well, then what is true about the world such that we're going to describe it this way, right? I do want to know what is true about the world. So I don't know if that was helpful, but yeah.
Hello, thank you.
Mhm.
So one of the most difficult to understand parts of quantum physics is the quantum measurement. And I think it's particularly interesting if you look at the hybrid system where you both have the quantum processor and the classical computer with feedback. So where the measurement goes into a classical computer, which is classical, and then goes back to the quantum system. My question is, have you thought about, can we, by making quantum computers and understanding quantum computers, better understand what is a quantum measurement and what is the basic physics of quantum measurement?
So, to be perfectly honest, I am not that optimistic that we're going to learn anything about the quantum measurement process that we didn't already know. Okay, because mathematically we can already perfectly well describe, all of this. Everything that you just talked about. I mean, and in fact, every quantum computation, as I said before, will be that kind of hybrid system, right? For several reasons. One of which is the error correction, right? A fault-tolerant quantum computer will involve constant rounds of measurement to see, the error syndromes, if there have been bit flips, if there have been phase flips, how do you correct them? So there will be this constant interaction between the quantum and the classical components, right? And people sort of worked out in the 1990s, exactly how that's going to work, exactly how it should work. Of course, we don't yet have error correcting codes that are practical enough that we can run them on the devices that we have. But I think that if quantum mechanics works the way that is written in the textbooks, then this ought to work, and we understand why it works. Modulo the philosophical questions about the measurement problem and blah blah blah. But it's not clear that having a quantum computer is going to answer those questions, right? People can still argue about the philosophical stuff in a world with a quantum computer just as well as they argue about it right now. So now there are, if you ask me to envision, how could the actual availability of a quantum computer, change the discussion of the measurement problem, right? Then there are a couple things that spring to mind. One is, of course, if the effort to build a quantum computer revealed any problem with quantum mechanics. Okay, if it revealed any breakdown of unitarity or breakdown of the Born rule or anything, well, I mean that would be a revolution in physics, right? And at that point, the fact that we had been trying to build a quantum computer would just be like a footnote, a historical footnote of like this is what led to this massive revolution in physics. Okay, and this is a point that I've always made to the quantum computing skeptics, right? If they say that quantum computing will fail because of something wrong with quantum mechanics itself, then that is way more exciting than a mere success in building a quantum computer, right? Like I don't expect that to happen, but if it did happen, oh my God, right? That would be so awesome, right? Now the other thing is just that, you could say, even though we can predict perfectly well on the basis of theory, what happens when you make a measurement at the end of Shor's algorithm and so forth. It might be that just actually seeing it and, seeing that it is a real thing, that might have a cultural effect. It might have a psychological effect. It might change the way that people talk about these things because it's no longer like, well, if hypothetically you did this, you factored this 2,000-digit number, then what would be the implications for, the many worlds interpretation or for the measurement problem or, the reality of this exponentially large vector of amplitudes, right? It would now be, no, someone actually has done it, right? That would now be an established fact. And so now the speculations can sort of jump off from a higher point than before, as it were.
So when you think about the hype cycle, arguably we can argue that we are now on the hype, right? But so my question has two parts. One, where do you actually think we are on that hype cycle? And two, when we think about the phase of disillusion, what do you think will be the main cause for that disillusion? Is it going to be the difficulty of manufacturing? Is it going to be the noise? Is it going to be the scalability? What do you think is going to be causing that disillusion?
Causing that what? Sorry, I missed the
The
word.
disillusion.
The disillusion. Sorry.
Disillusion.
The disillusion.
Yes.
Like disillusionment.
Yes.
Ah,
So like
yeah.
hype and
Okay. Okay.
disillusionment.
Okay. Yeah.
Sorry for my.
It's all right. No, it's fine.
But did you get a question?
Yeah. So, so I think that this is a period of staggering, unbelievable, gobsmacking, level of hype. I mean, like I start, my blog around 2007 or so. I started trying to push back against quantum computing hype. And I would say that the level of it was maybe like 1% of what it is now, right? And ironically, I do a lot less of it, right? But that's just because there's too much of it, okay? I can't deal with all of it. I can try to say what I think is true when people ask me, but I feel like I no longer can be, I no longer can sort of jump up and down, and get exercised every time I see someone else say something that's false. Okay, there's just because otherwise, I just can't do it. It's too much. So, I mean, there are now there's more than 100 quantum computing startups, I guess. And and some of them are actually doing very interesting things, and some of them are have really good people, and I hope that they succeed. And there's there are companies are now treating this not as just like a blue sky research thing, but as like a major part of at least their rhetoric of what they're going to do in the future, and that's Google, Microsoft, IBM, Amazon, and others, as we've heard from, right? And it has become an issue of national security, right? Of the EU, the Chinese government, the U.S. government, investing in this as sort of as a matter of maybe national prestige, national competitiveness, right? And and part of me is really excited about this, like because like we knew from the beginning that if you want to build a fault-tolerant quantum computer and really have it work, that is going to be a massive engineering project, right? Probably it would cost billions of dollars, right? And now we are having the world is having a real go at it, right? And as I said before, if we fail, then we will not have been able to say that it was for lack of trying, right? On the other hand, often, when I talk to people in the business world, or the investment world, right, or the government world, right, who have made or are making big investments in quantum computing, and I talk to them about why, there's just like this world of beliefs that is just in direct conflict with what we in quantum computing theory have known since the 1990s. And they'll start talking about the exponential speedups for the traveling salesman problem, right? Still, people talk about that. They talk about exponential speedups for all of these machine learning problems, and that we're going to achieve all of this in the NISQ era, and and we know that all this, and and we'll use quantum neural networks, and those will get speedups, and I'll say, well, actually none of that is true. And they'll say, well, that's an interesting opinion. I see that you have strong opinions about this. And I'll say, no, it's not an opinion. It's just, talk to any of the experts, and they'll say that exactly the same thing. Somehow, so it's this sort of bizarre situation where sort of, we all know something, and and we all tell the truth about it, and yet, somehow, what gets heard is sort of different from what is said. So I don't know what to do about it. But I accept to just continue saying that yeah, we expect big speed ups for quantum simulation. We expect big speed ups for, for breaking public key cryptography, and eventually we hope for more modest speed ups for other things like optimization, like machine learning. And we continue to discover more about what quantum computers are good for. But exactly as Umesh said in his talk this morning, right? I thought it was really great. Like we should sort of give the devices a little bit more room to breathe. Like look at what they are naturally doing or what they are naturally good at, and then try to figure out whether that's also useful for something, rather than starting with, well, I want to speed up this optimization problem. I want to do this for financial derivatives, or this for the oil and gas industry. And now how can I make it look like quantum computing is going to give a speed up for that? Or how can I shoehorn quantum computing into that? I think that you can try that. It's great to, if you can make it work. But empirically, that has been less successful than just starting with what the devices naturally do, and then trying to figure out what it's useful for. So to the second part of your question, which was about disillusionment, it's kind of like I keep thinking, like if this is what we who study this for a living know, and and then this completely other thing is what people who are enthusiastic about it believe, then at some point there has to be a collision, right? And I keep being wrong, because year after year there's no collision, right? And it just the enthusiasm continues. But it's kind of like Bitcoin. I say like Bitcoin is at $10,000. Well, that's completely ridiculous. I would never buy such a thing. And then the next year it's $50,000. So I guess I was a fool. So at that point I just throw up my hands. I don't know what to say anymore.
Just continuing on those lines.
Yeah.
Just continuing on those lines,
Yeah.
we hear that RSA 2048 will be broken in 5 to 10 years. It does not seem, it does not agree with the technology roadmaps that we see. What's your take on that?
So I have no idea. So I don't believe in roadmaps, for a subject like this, right? Because you can try to plot out what's going to happen for the next 10 years, and then my experience has been that in 1 year or in 2 years something happens and it changes the situation, right? I've the few data points that I have about how long things take in this subject are from interacting with my experimental colleagues, around quantum supremacy. First around boson sampling, and then around random circuit sampling, so they would say, well, this is actually an easy experiment. This could be done in the next year, no problem. And if they say that, usually it's like 4 years, like 5 years. So then I kind of have in the back of my head, okay, I guess the multiplier is to apply is 4 or 5 to whatever they say, right? But it's not infinity, right? The things that they told me, could be done, like boson sampling with 50 to 100 photons, random circuit sampling with 50 or 60 qubits. Those things now have been done. Okay, admittedly, not with the error rates that we want, right? And again, Umesh talked about this, right? That the error rates are still such that there are classical spoofing attacks that are competitive, and we would like to get past that. We'd like to get to the point where there's no longer any argument, and that will still take some time. But I would say that if you have secrets that and it's really, really important that they stay secret for the next 5 or 10 years, then maybe already you should not be using RSA, right? And that's not because we can have any confidence that someone will build a scalable quantum computer in that time frame. It is only because we can't have confidence that they won't. Okay, and all the more so if we make that 15 years or 20 years or something like that. Okay, but at the end of the day, if I had any ability to forecast how long these things would take, I would not be a professor of computer science. I would be an investor, and I would be rich.
First, thank you for sharing kind of your insights on the simulation and optimization parts. There's actually one more kind of primitive or so like interactive proofs that is not a big focus of attention, but that essentially, I mean, with classical capabilities like zero knowledge proofs or other things, is interesting for anonymous computing or so. What is your opinion? Like, what is interesting there? What's coming up?
Well, okay, so I can say that some of the most exciting theoretical developments in quantum computing in the last 3 or 4 years have been around the subject of interactive proofs. Okay, we saw Urmila Mahadev's protocol, right, where she solved an open problem, that I had popularized on my blog, actually, of how can a quantum computer always prove its answer to a purely classical skeptic? And she did that, via like a tour de force, use of post-quantum cryptography. We've seen, at a more theoretical level, right? We saw this enormous breakthrough, this MIP star theorem, just a couple of years ago, showing that 2 entangled quantum provers can actually convince a fast classical verifier of the answers to the halting problem, right? That an arbitrary Turing machine halts. And you're right. I actually could have mentioned that when I talked about the potential uses for quantum computers. Even if you just wanted to do a classical computation, it is conceivable someday that if you wanted it to be blind, for example, if you wanted to delegate your classical computation or quantum computation to someone else and have them verifiably do it and have them learn nothing about which computation they did, then you might want them to use these blind quantum computing protocols. Now, I expect that it'll be quite a while before we actually get an advantage this way, just because the overheads are so large, right? And especially if we need to use one of the cryptographic schemes, like Mahadev's, right? Then we have to do this public key cryptography, basically this learning with errors cryptography on superpositions of inputs. And we have to be maintaining the superposition while we exchange messages between the prover and the verifier. So that looks very expensive. That looks like, in an eventual world with fault-tolerant quantum computers, we'll be able to do that, but probably not before then. And I always have to add here, unless there's a further breakthrough in the subject that makes it practical.
What type of philosophical questions do you hope that quantum computers would eventually be able to address?
What kind of what questions?
Philosophical questions. So I heard something about quantum computers and free will that you talked about before. Maybe something like this, or maybe some other questions that you are excited about?
Well, I mean, I would say that whatever philosophical questions we can ask once we have a quantum computer, we can already ask those questions now, before we have the quantum computer, right? That's the thing about philosophy, right? You don't need the actual device to start wondering about things, right? And people have been asking philosophical questions about quantum mechanics for as long as there has been quantum mechanics, right? I mean, Bohr and Heisenberg, and many others were already immediately, like the ink wasn't dry on the Schrodinger equation, right? Before they were talking about what does it mean philosophically, okay? So, the speculation that there might be some sort of connection between quantum mechanics and free will, again, that is as old as quantum mechanics itself. Right, and it's very obvious why that idea would arise, because quantum mechanics is the one thing in fundamental physics, that at least appears to violate determinism, right? At least, once we incorporate measurements, right, then it says that there is randomness, there is indeterminacy at the, most fundamental level of nature. Now, the difficulty with relating that to free will in the human sense is also obvious, and also goes back to the 1920s or 1930s, and the difficulty is, well, just because, you might not be able to predict exactly when this radioactive atom will decay, let's say, but you can calculate very precisely its distribution over decay times, right? And that just does not seem at all like what we mean when we talk about free will, right? Would we say that atom that decays randomly with a certain half-life? Would we say that it has free will? Well, what is added by saying that? I think more interesting maybe is the fact that even in order to make a probabilistic prediction about what a person is going to do, you would need to know the state of their brain to an enormous level of detail, right? And because someone making a decision might ultimately be traceable back to a single neuron firing or not firing, right? And that neuron might fire because of a single, because of some sodium ion channel in the axon, which is open or closed, right? And that could ultimately be because of some random molecular jostling around, and ultimately because of some chaotically amplified quantum event, right? And so, just in order to predict the probability of someone doing something versus something else, which we know is all that you could hope for in principle, right? You would have to, it seems, know the quantum states of all of the atoms and all of these sodium ion channels, right? And maybe, that is something that you just can't get without, destroying the brain that you're interested in predicting. So, I think these are interesting things for people to argue about if they're wondering, like, can an exact copy be made of you? If it happened, if that were done, then what would happen to your consciousness? Would it split? Would it go over to the other copy? Would you agree to be to have a copy made of you, and then maybe the original copy will just be painlessly euthanized, and would you agree to have yourself teleported in that way? These are old philosophical chestnuts, right? But at some level it comes down to the question of how high fidelity does a copy have to be before it's really you, right? And before it really makes the same decisions that you would have made. And is it enough to just copy the classical, the sort of macroscopic information in the brain? That would be one very reasonable working assumption. And if so, then none of the underlying physics would matter. But if you needed more detail, well, then ultimately you would be up against the no cloning theorem, right? So, those are some of the fun philosophical debates that you can have around quantum mechanics or personal identity, free will. I'm not sure that any of it really has to do with quantum computation per se, though.
Yeah, so talking about quantum complexity theory, in your opinion, what are the most interesting open questions here, and are there any implications of discoveries in these areas?
Yeah, so I think the biggest open questions of quantum complexity theory, we're asked, near the very beginning, like when Bernstein and Vazirani, defined the class BQP, quantum polynomial time in 1993. They asked things like, well, is BQP larger than BPP? In other words, can a quantum computer solve any problem in polynomial time that a classical computer cannot? And we might strongly believe that that is the case, for example, because of Shor's algorithm, but no one has proved that factoring is not in BPP, right? So we don't actually know that, for all of the problems that admit that admit these fast quantum algorithms, we can't currently prove that any of them are require exponential time classically. We only conjecture that. Okay, one could ask, is NP contained in BQP? That is, can quantum computers solve NP-complete problems in polynomial time? Again, most of us would conjecture that the answer is no, that for NP-complete problems, typically you can get the Grover speed up, and probably not a whole lot more than that. But there's no proof. Okay, one could ask, what is the best upper bound on the power of BQP? So is BQP contained in NP? So when a quantum computer produces some specific answer, is there always a short classical proof that that was the answer that a classical computer can then go and verify? And which would not require an interactive protocol like Irmila Mahadev's. Okay, so those were all open questions 28 years ago, and those remain, I would say, the guiding questions of quantum complexity theory today. It's just that usually today we don't directly address those questions because it's just too hard to say anything new about them. And so then we address other more subsidiary questions, more auxiliary questions. Now you could say so maybe the right thing to ask is not what are the biggest questions in the field, but what are the biggest questions that we have an actual chance of answering, let's say, the next 5 years. And there, I've got some personal favorites. I still really like this question of QMA versus QCMA, which basically is, are quantum proofs more powerful than classical proofs? Can I prove something to you by giving you a quantum state, of n qubits, where if in order to prove it by giving you a classical string of bits, it would have to be an exponentially larger string, even assuming that you're allowed a quantum computer to verify the proof in both cases. And what's interesting about that is that we don't even have at least a conventional oracle that separates QMA from QCMA, which is usually our just sort of minimal kind of evidence that one model of computation is more powerful than another one. So I would love for someone to find that oracle separation. And there's a lot. I actually just wrote a survey article about my favorite open problems in quantum query complexity, which you could take a look at. So yeah, so there's a bunch of other nice problems. I would like to know what is the power of QMA2. That is, if I get 2 quantum proofs and I know that they cannot be entangled, then does that let me do a lot more than if I have only 1 quantum proof? And amazingly, as far as we know today, if you get 2 unentangled quantum proofs, maybe that lets you do everything in non-deterministic exponential time. So that might just be ridiculously powerful. I don't think we have any evidence against that possibility. And I would love to know whether it's true or false.
Is there any area in quantum technology that you think is being ignored and should deserve more attention and funding?
Let me think about that. I mean, I'm very interested in in fundamental tests of quantum mechanics. I'm very interested in can we create large Schrodinger cat states? Can we put a big mass in superposition? Let me just think a little bit. The truth is that as soon as someone has takes an idea down to the level of hardware, right? There's probably already a startup for it, right? And that startup has probably already raised more venture capital than I'll ever see in my life, right? So it's a very strange situation that we're in right now.
So Scott, if we end right here, I think a lot of people in this room are going to go home very depressed, right? Scott Aronson says there's no hope. So
when did I say that?
Well, like the quantum computing isn't ever going to do anything, or
of course it will. I fully expect that it will factor 4,000 digit numbers.
So where is hope for all these companies that are doing things today? There's all this energy out there.
Yeah, I mean, the hope is that someone will really solve the hard problems of scalability and fault tolerance, and that having solved them, that we will then have a new window into nature, into doing quantum simulations, and maybe eventually into getting some modest speed ups for optimization problems, and hopefully something else that no one has thought of yet.
So, okay, good.
No.
So maybe the last question or comment. I just want to say that, Scott, I think maybe there was a little bit of misunderstanding on some part, that when you mentioned about application and optimization in machine learning, saying that you don't see much of a promise on classical optimization and classical machine learning, you left out a potential window for relevance of quantum computers, which is when you do machine learning on quantum data, which is the same nature as quantum simulation, because quantum data needs exponential, it is exponentially expensive to represent class. The model are basically inefficient classically. So that actually there's a paper we just put last week on that. So I just want to let you to correct that. I know that you're aware of
I think, I am aware, and I do think that by far the best hope of getting exponential quantum speedups for practical machine learning problems is for problems that themselves involve quantum data. That's not usually what people mean when they talk about machine learning applications, but I completely agree with you there.
Okay, thank you very much. Let's thank Scott.